Hi, in this lecture I will be focusing on the Z transformation, which is used for the analysis of discrete linear time invariant systems. Basically we have two kinds of signals, one is continuous and other is discrete. In continuous the time is continuous and the signal is represented for all time values, and the independent time variable is t, and its graphical representation is this kind of signal, which is represented for infinite values of t, the signal amplitude y. For the discrete signal the time is discrete. The signal is defined for some splitted intervals, and independent variable is the sample, which is n, and its graphical representation is that amplitude is represented for some discrete and finite samples of time. If we talk about Z transform and its inverse Z transform, then the formula of Z transformation is this one. Here xn is the discrete time signal and xz is its Z transformation, and it is represented by summation minus infinity to plus infinity and xn into z minus n. So this formula is used for the Z transformation. If we talk about continuous time, to convert it into frequency we use either Fourier transformation or Laplace transformation. This is Laplace transformation is a complex frequency representation. It is another frequency representation which is not complex. And if we talk about discrete time, then to convert it into the frequency we use the discrete time Fourier transformation or Z transformation. This is a complex frequency representation, and this is other frequency representation. For the Fourier transformation we use this formula for integral minus infinity to plus infinity. This is a definite integral into xt into exponential term into dt, and it is giving us a continuous frequency representation for a continuous time. And if we talk about the discrete time Fourier transformation, it is also giving us a continuous frequency representation with summation terms from minus infinity to plus infinity. If we talk about the relation between the dtft and zt, then if we have the formula of Z transformation, this one, and we put this value of Z, which is real number, into exponential term by taking anticipation from the dtft, and we put that value in terms of Z and we rearrange it, as we all know that dtft of xn is this one, so we can uh, take note from it and simplify the above relation into this form. And if we take the inverse Z transformation, then after rearranging the values we get a kind of relation, this one, and here we have to change this relation to dz, and we, after doing some this exercise, we change this relation to dz and we arrive with inverse Z transformation relation. So this is a relation for the inverse Z transformation in which we give the value of xz and we get the value of xn, while the previous relation, this one, is the relation of the Z transformation where we give xn and we get xz. Okay, now we can focus on the examples. If we talk for some finite sequences, and we in these examples we will do the calculation of the Z transformation for some finite sequences. Like this is a finite sequence, this arrow is indicating the value at the 0 point, and these are the uh, past values and these are the future values, and we are going to find the xz of that finite sequence. Then we can see that we have this formula, and we can put the values in that formula from minus 2 to 3, and we put the value of xn, and then we can solve it, and we can see that we have this Z transformation xz for this xn finite sequence. Another example, this is the 0 value, these are the future values. We get the formula of the Z transformation written 0 to 5 sample, we put the values of xn and we get the z transformation. So now if we want to get the inverse z transformation, we can see that this is the xz and we want to get xn, and we have this formula, but this formula is giving some complicated and complex calculations. Firstly, we see that either xz is in a form which is a kind of can be converted in an easier way by taking into account the formula of the z transformation, and if that's not the case, then we can use that formula. So if we write xz, then we can see that the positive values indicate the negative terms. If we take some if we observe that formula of the z transformation, then the future values will be containing the z negative value, and the z0 value will be the present value, and z plus values will be the past values. So by taking into account this formula and by looking at this xz, and we can see that this sequence is from -4 to 2, and we can see that we can directly convert from xz to xn by just getting their coefficients, which are 4 1 0 3 0 4 3, and we can convert it directly by observing the formula of the z transformation instead of using this complicated formula, and we can convert it into xn. Similarly, this is another example, and we can see the positive value of z indicate the negative term, and there is no present term, and there is no term which is of -1, and there is only one term of z0. So by taking into account this formula, and we can convert directly from xz to xn, and same is the case over here in this example, where we do the same process and we do the conversion of the xz to xn. Now we will be doing the conversion of xn into xz, and for some known signals, some kind of signals, like for example, if we have this signal and we have this signal and we want to take their z transformation, and these are xn values, then firstly we take this value and we put that value in the z transformation formula, and we can do what is that over here ax we know that un is from 0 to infinity, and we uh, this un will limit this summation limits from 0 to infinity, and then we are rearranging it. We have this formula, we use that formula to do further simplification, and we get the xz over here. So another xn or yn is this one, and we put this in the formula of the z transformation, and this has changed the limits, the un from 0 to infinity. We are doing the rearranging, we have this formula, and we are doing the simplification, and we get the yz over here. Now there is another term of xn, and we want to get its z transformation. Then we put that xn in the formula over here in the z transformation, and we know that u minus n minus 1 is from 1 to minus infinity, if we see these two behaviors as well, and it will be changing the limit from minus infinity to 1, and then we will be doing the rearranging of the values, and we have done the reversal of the limits to change the sign outside over here, and then we have added and 1 and -1, and both are of the power of az into 0, and the added one will be digest in this value to get its limit from 1 to 0, and then we will be using this formula which is applicable for 0 to infinity, and then we will be doing the simplification and get the xz term. Similarly, by taking light from this expression, we can directly convert this into this. Now we will be doing the z transformation for xn of this value. Put that value of xn in the z transformation formula, and we know that u minus n minus 1 will be minus infinity to 1, and then we will be doing is that we are having this relation, and for this, in order to use that relation, we have to have it in this form, and so that then we will be doing the reversal of the limits, which will be changing the outside sign. We are rearranging the negative signs of z and a, and then we will be adding 1 and minus 1, and adding 1 will be digest in that limit of z a minus 1 raised to power 0, and it will come over here, and then we will be using this relation, and then we will be doing the LCM and further simplification to get the xz. So now there are some other properties of the Z transformation: the linear property, the time shifting property, the time reversal property, the scaling property, the differentiation property. These are very much frequently used in the Z transformations or the inverse Z transformations. Now we will be looking at about region of convergence of Z transform. The region of convergence in Z transform is indicated by the unit circle over here. If xn is a right-sided sequence and the Z is equal to real number in the region of convergence, then all finite value of Z for which Z mod is greater than R will also be its region of convergence. As we can see over here that we have, this is a right-sided sequence, and by taking its Z transformation we have this value, and then we get from denominator Z is equal to R, and it is a right side sequence, so the region of convergence of the Z will be greater than R value. This is the unit circle, this is Z is equal to R, and it is a right sided sequence, so all the values of Z greater than R will be the region of convergence. Similarly over here, this is a left sided sequence, xn into u minus n, because it is a negative sign, xz comes this, and then we have z is equal to R, but the region of convergence will be, because it is a left side sequence, will be all the values of z which are smaller than R. So if it is a two-sided sequence, like right-sided or left-sided sequence, positive and negative signs, and its xz is this, then the region of convergence will be of radius r, which is limited by this function, and it is R, the region of convergence. Similarly, if we have the right-sided and the left-sided sequences, and there are rational numbers, and then z is equal to 2, z is equal to 3, it is right-sided, so region of convergence greater than 2. It is left-sided, so region of convergence smaller than 2, which will be in between, and it will be limited by the poles in between. Between 3 and 2 will be the region of convergence. Okay. So if we have a right-sided sequence, both are positive, then the region of convergence will be greater than 2 and greater than 3, and will be outside the greatest pole. The greatest pole is 3, so the region of convergence will be greater than 3. All the values of z greater than 3 will be the region of convergence, because it is a right-sided sequence. And if we have the left-sided sequence, both having the negative signs, then the region of convergence will be smaller than 2, smaller than 3, and will be in between the smaller most pole. In this case we have 2, so the region of convergence will be within 2 all values of z. Now for the causality, what is the condition is that the common region of convergence would be the exterior of the outermost pole, because if we have two poles and the one pole is greater than the other, then the common region of convergence should be greater than the greatest pole. This is the one condition for the causality, and the other condition for the causality is that if we have Z transformation happened for any xn or hn, if we have hn and we have done its Z transformation as hz, and we have a kind of number which has a numerator and a denominator, then the power or the order of the numerator cannot be greater than the denominator. Like we see, if we have a right-sided sequence and we have 2, z is greater than 2 or z is greater than 3, it is a right-side sequence, and the region of convergence is the outermost of the greatest pole, which is 3. While if we see its kind of transformation, it is like this value, then it is causal, because the highest power of the denominator is greater than the numerator. But in that case, the numerator is greater than the denominator, the power, so that is anti-causal system or non-causal system. For the stability, we have some condition. It is the condition which says that once we get the hn, and we from hn we get the hz, and from hz we get the pole, and from the pole we get the region of convergence, and if the region of convergence contains the unit circle, then it is a kind of stable system. And we can say that a casual linear time invariant system is stable if and only if the outermost pole uh, is having the unit circle. So we can see that a casual linear time invariant system is stable if and only if all the poles of the HZ lies inside the unit circle. So in that case only will be the greatest pole containing the unit circle, like for this case in which we have the greatest pole is 2 by 3, which is within the unit circle. So if all the poles within the unit circle, then the system will be stable and causal as well, while for the stability it is the only condition that the region of convergence is containing the unit circle. Now we have to have some examples of detecting the stability and the causality of the system from the Z transformations with the help of region of convergence. Now we have a condition in which we have a system whose equation is this one, and it is a right-sided and the left-sided sequence, and we want to detect its Hz. Then its Hz will be like that, taking note from these kind of formulas, and it is right-sided, so region of convergence greater than 1 over 3, and it is a left-sided sequence, so region of convergence will be smaller than 2. Then it will be in between these two, and this region of convergence is containing the unit circle, so it is a kind of stable system. Okay, so another thing we can see that the denominator is not greater than the numerator, so we can say the system is anti-causal. Okay, or we can say that common region of convergence is not exterior to the outermost pole, so because it is in between these two, for the causality condition we have to have all the poles within the unit circle, or the common region of convergence is greater than the outermost pole. So it is not the case, so we can also say that it is a kind of anti-causal system. Then we have another system which is expressed by this equation, and this is a right-sided sequence, this is a left-sided sequence, and we from this formula get the Z transformations, and for this the region of convergence is smaller than 1 over 2, for this the region of convergence is greater than 1 over 3, and we can say that the common region of convergence is not happening for both these, and we have a unit circle which is over here, but there is no common region of convergence, so there is no region of convergence which is common, so the system is not stable and causal. Thank you very much.